Welcome to today's panel discussion on innovation with diamond technology, hosted by RFHIC. RFHIC is the world's first and only GaN, RF, and microwave transistor to subsystem solution provider for various applications in wireless infrastructure, radar, and RF energy. We do provide a broad range of commercial, off-the-shelf, and customizable products operating from DC to 40 gigahertz with power levels up to multi-megawatts. So first, for some introductions, I'm Grace Cho. I'm the Strategic Planning Marketing Team Manager at RFHIC, and I have the pleasure today of moderating today's session. And today I am delighted to be joined by 5 of our tech panelists. So first, Daniel Twitchen, who is the Chief Technologist at Element 6. Daniel carries over 25 years of experience in developing CVD diamond synthesis for optical, thermal, electrochemical, and sensing applications. And he leads the E6's quantum program and commercial CVD team. Stacey Armagost, who's the VP of IR Optics and Materials Division at II-VI. So Stacey has over 30 years of experience in optics and materials, and she and her team are focused on developing new capabilities and products enabling higher power industrial lasers, thermal management solutions, and next-gen EUV systems. Next, we have Dr. Phillipe Bergonzo, who's the VP of Seki Diamond Systems. Dr. Bergonzo is responsible for promoting diamond synthesis and equipment distribution for the expansion of diamond technology. And Seki is a leading provider of CVD diamond reactors, offering a broad selection of microwave plasma, hot filament, and low temperature CVD systems. Next, we have Professor Oliver Williams. He's a professor of experimental physics at Cardiff University, and he's also the head director of research at Cardiff Diamond Foundry. Oliver works on applications of diamond films and particles ranging from CVD growth of thin films to bulk materials. And last but not least, Dr. Wenzong Li. He's the director of Ganon Diamond Division at RFHIC. Dr. Li has over 30 years of experience in gallium nitride. He and his team are developing the world's first high-power Ganon diamond Hemp for commercial production level performance. Hello, folks. How are you all doing?
Very good, thanks.
Very well.
All right, super. So, well, thank you so much for joining me today. But before we do jump into our session, let me say a few housekeeping updates for our audience. So this webinar is being recorded and will be available for all registered attendees within the next 24 hours. And also, if you have any questions throughout the webinar, please do upload your questions to the Q&A chat room to the side of the screen, and we'll definitely address those during our Q&A session at the end of the webinar. And specifically, we do recommend you, when you do ask a question into the chat room, that you specify a specific panelist that you would like us to address the question towards. And if we don't get to answer your questions today, we will definitely have a member of our team reach out to you within the next couple of days with an answer as well. So I guess with that settled, here's the agenda for today. So I guess I'll start by giving our audience just an overview of our topic, and then I'll let our panelists present with their insights about the futures of diamond technology to their respective applications by answering some of our questions. Like I mentioned before, we'll have time at the end for some audience questions towards the end, so please do send them in now, and we'll have a chat to those later on. Great. So I guess a short overview of our topic on diamond innovation. So I guess very many of you probably know the famous saying, diamond is a girl's best friend. But in recent years, that phrase has definitely caught on within the tech industry, and especially the semiconductor industry. And that phrase has kind of changed to, diamonds are an engineer's best friend. Diamonds are a high-power engineer's best friend. And the diamonds that we're referring to are synthetic diamonds that are grown either using high pressure, high temperature, which is HPHT, or chemical vapor deposition, which is also commonly referred to as CVD processes. So I guess, when we get past that, romantic notion of, diamond is one heck of an engineering material. Diamonds are the hardest material known to mankind, and, they make a very excellent abrasive and protective coating for, various applications, from industrial tools to, kitchen work surfaces. So also for, semiconductor or electronic applications, diamonds are known to dissipate heat more rapidly than commonly used materials such as silicon within the semiconductor industry. So a lot of researchers are definitely developing ways to implement diamond into their chip making processes, allowing them to get more components on a smaller surface while maintaining excellent efficiency and high power levels. So I guess with that overview set, I'm going to set the scene by kicking off our first question to Stacey, who is the VP of IR Optics and Materials at II-VI. Stacey, could you tell me what is it about diamonds that makes you and your team passionate?
Okay, so thank you, Grace, for hosting. For II-VI, we are the company where materials matter. So this material, we have a long history, 50-year history almost at II-VI, and it's really started with the base materials and through vertical integration. So for diamond, because of the unique properties, as you've already mentioned, the hardness, the broad transmission specifications, we believe that this material hasn't even started to see the full potential that it has. So our co-founder, Carl Johnson, actually called this the 100-year material. So I think that's a great quote to kind of think about, because, usually there's a lifetime with materials. They can be replaced by other materials, but I think it's going to be difficult given the properties and the uniqueness that diamond has to be able to replace that anytime soon. So we're excited about it because we see a broad range of application, whether it's thermal, optical, mechanical. I think there's a big future for where diamond is going to go. So we're excited about it, and we think it has a lot of potential.
That's awesome. Thanks for that. I also want to throw kind of the same question out to Dr. Phillipe Bergonzo, who's the VP of Seki Diamond Systems. Being a leading provider of CVD diamond reactors, what are kind of some of your thoughts on diamond that make you and your team passionate at Seki Diamonds?
Well, thank you, Grace. And well, basically the remarkable interest for diamond is really the diversity of the materials you can grow, you can synthesize. Diamond can take a lot of aspects and shapes, and it's very important to be able to tune this shape according to the way you can exploit the geometry or the characteristics you want to take into your device. You can fabricate diamond to make electronic devices, like Stacey said. I spent a lot of my time making radiation detectors when I was doing research. Diamond is also very good to make quantum sensors. I guess probably Danielle will mention about this, or electrochemical sensors, heat spreaders, and so on. Probably the 5 panelists around the table, we all have very different background and very needs for different types of materials. And today, it's very difficult to grow, a big cube of diamond like we do for the semiconductors. We cannot grow crystals of 30 centimeter diameter like we do for silicon. So we always have to optimize the dimension of the synthetic layer we fabricate according to the performance we want to use. A quantum sensor is very small. A heat spreader has to match the size of your substrate you want to cool. Therefore, it can be 4, 5, 6, 8, 12 inch. Why not? A biological implant can be very thin. 10 micron will be enough, but it needs to be very flexible. And this is this diversity that we work on at Seki Diamond System to make sure that our reactors are able to provide tools for people to be able to fabricate those materials and help our customers to really grow the material they need and of course the properties they want to obtain from these materials. So it's this diversity that is very crucial for diamond.
Oh wow, that's fascinating. Thank you for that. So to move on to question 2, I know I touched base on this a little earlier, but I want to get an expert's point of view on this. So Daniel, do you think you can kind of briefly explain to me or to our audience about lab-grown diamonds in terms of how they're processed and how kind of they can be used for various electronic applications?
Sure, sure. Thanks, Grace. So really, there's 2 parts to that question, and the first enables the second, and the second we've heard a little bit about some of the applications, and I'll talk about that in a moment. But the first really was the development and synthesis process. So to tap into diamond's remarkable properties, you need to be able to grow it reproducibly. And the key for that really over the last 20 years has been progress in growing diamond using chemical vapor deposition techniques. And in its simplest form, you create a hot gas. That hot gas is full of hydrogen and methane. And if you like, the magic trick is breaking down the molecular hydrogen into atomic hydrogen, and then you can deposit carbon on a much cooler substrate. The carbon goes down both as graphite and as sp3 as diamond, but atomic hydrogen etches away the graphite much faster than the diamond. And for 30 odd years, people didn't believe you could even grow diamond in this part of the phase diagram. But by developing those techniques, it's been possible to actually grow wafer scale diamond. And here's actually a thick piece, about 2 millimeters thick piece of diamond, 100 millimeters across. And the properties of that diamond, probably less than 0.5% of natural diamonds match. So natural diamonds, by the nature of their growth process, have properties that are often a long way away from perfect diamond. By developing chemical vapor deposition techniques, it's been possible to tap into those perfect properties of diamond. Again, with the chemical vapor deposition technique, you get all the benefits. You can add things into the gas phase, dope the diamond. So, for example, while this is obviously transparent, this wafer here is opaque, and the difference here really is I've added a lot of boron to the gas phase. Now all of a sudden this wafer is conducting. So it's an interesting, robust electrode. So that progress in synthesis, and you heard Phillipe talk a little bit about hardware earlier, has allowed engineers and scientists to begin to really tap in reproducibly to the material properties. We've heard a bit about those material properties earlier, but thermal conductivity. The thermal conductivity of diamond is more than 5 times higher than copper. It can exceed 2,000 watts per meter per K. It's a wide bandgap, so if you need to hold off a high voltage, you can sustain a high voltage. It's low density, so if you think about electronics, sometimes weight's a factor, especially if you want to put electronics in space. Size, weight, and power matters, so the density is low. Chemically inert, so what makes this electrode so interesting? Yes, it conducts, but in solution, you can produce very powerful oxidants, and those oxidants can be used to break down organic waste, byproducts of maybe the pharmaceutical industry, or to sanitize your desk even. But the great thing is the diamond is inert, so actually it doesn't erode. So you get the performance and also the lifetime. And I'm sure Wan Sang's going to talk more about the thermal applications, but when we talk about data, we all take data increasingly for granted. Data is the new utility. Wherever we go, we can download email, we can download a Netflix movie. And really at the heart of that is gigabytes of data per dollar. And the advances in technology has enabled that. And one of those significant advantages which RFHIC are really with the forefront is gallium nitride. In some of these gallium nitride transistors, the power densities are in excess of tens of kilowatts per square centimeter. Even as a physicist, when I try and comprehend what tens of kilowatts per square centimeter is, it's phenomenal. But to really get the full potential from that GaN device, you've got to dissipate that heat. So if you can get the diamond close to that heat source, the best conductive heat can dissipate that heat. And of course, in device terms, that means you can push more power up, you can get a better linear device. Reliability, more than 50% of failure modes in electronics is still heat related, so you get more reliability. So diamonds, remarkable properties being accessed through this CVD technique, and then all of a sudden now we're starting to see them being used.
Oh, that's awesome. I think I just learned so much more about diamonds from that explanation. Thank you for that. So, Dr. Lee, from a high power RF and microwave applications point of view, what are kind of some of your thoughts on lab grown diamonds that maybe Daniel didn't touch base on, and what are kind of the types of impacts that that they could have for the RF and microwave field?
Okay, thank you for invitation. I fully agree with the Daniel's opinions. As you knew that, using diamond technology, RFHIC has a plan to using power amplifier solution in the area of high frequency microwave systems. To adapt this application, diamond should be make round shape, the Daniel showed, the round shape wafer for semiconductor processing. So I believe that such a method of lab-grown diamond technology is an only solution to make our goal. Currently, lab-grown diamond can be possibly make 4-inch wafer size as well as maximum 6-inch wafer size with acceptable the cost of industrial application for microwave and RF application. For example, currently lab-grown diamond can be possibly easy to making around 1500 watt per millikelvin thermal conductivity, but in the future we can be possibly make up to 2000 watt per millikelvin. If we can get such kind of that, the goal, we can get a lot of benefit in terms of reduce the power consumption, increasing efficiency, stuff like that. So I believe lab-grown diamond is our future. It's a key factor to improving all of the application in the semiconductor field.
Okay, right. Thank you for that. So, I mean, it definitely seems like, diamond is being sought out, by physicists and engineers, worldwide. So I guess, Oliver, coming from an academic standpoint of view, what are kind of some of the diamond features that you see being important that, maybe we haven't mentioned thus far, and that's kind of respective to your application?
Okay, thanks, Grace. I think Dan did a very good job of going over a lot of the properties. So if I was to pick one thing that sort of ruled them all, it would probably be the atomic density of diamond, because so many things kind of fall out of that. And if I can have 1.5, I'd say it's that plus the fact that it's carbon. So because you have this extremely dense lattice of carbon atoms, it's very hard. I think everyone sort of knows that. But there's a bunch of other consequences from that. So one is the thermal conductivity, right? So this is extreme. Dan's already pointed this out. But what a lot of people don't appreciate about that is it's the only one that I'm aware of that has a high resistivity at the same time. I mean, the next best is aluminium nitride, which is 1/5, and that's a huge drop. So you have an insulating material electrically that is very, very, very conductive, and that's highly unusual. The other thing that falls out also from this short bond length, from the fact that the little carbon atoms don't weigh very much, the low density. So like Dan mentioned, it's low density, but it's high atomic density, right? It's just the carbon atoms don't weigh very much, right? Is that the acoustic wave velocity in diamond is very, very high. So as I'm speaking to you, I mean, if we ignore the internet for a minute and pretend we're in the same room, the sound would be moving at 300 meters per second, but in diamond it's 20,000 meters per second. And so this has a huge consequence because you're able to operate very high frequency filters. You'll be able to make devices that vibrate very, very quickly. And I think this is very interesting for physicists. The final thing would be to go back to the sort of quantum technologies. I mean, one of the advantages of having a very dense lattice is that impurities don't readily go into diamonds. So if you think, back in history, one of the reasons why germanium failed as a semiconductor, well, failed is a bit harsh, but, was taken over by silicon. One was a native oxide. But the other one is that actually germanium, as it's further down in the periodic table, actually suffers from really purity problems. It's actually quite difficult to grow germanium very high purity. Which if you look at the results of element 6, whatever, in high purity diamond, they're really staggeringly pure. And this is, I think, in a quantum point of view, very, very important. That and the divide temperature, which I think I won't say any more about that. I think I'll leave it for Dan later. But I think the main thing for me is this bond length. Yeah.
Okay. Well, that was very insightful. So, I mean, after hearing a lot of your answers, it definitely seems like, diamond's key characteristic is definitely, its toughness. So, being able to withstand such, harsh environments, whether that be, high temperatures or high pressures. But, on the flip side of things, being the toughest material known to mankind, I would think that it comes with a lot of, challenges in terms of handling such a material. So, Stacey, could you kind of share a story of some of the biggest challenges that maybe, your team have faced, in terms of handling this material?
Sure, Grace. So, very good question, because, the material's one thing, but getting it to the end product is really the key, what the customers care about. So, 26 has many years of experience with diamond, but, one of the challenges was, first of all, we're a vertically integrated company. So, the growth of it through the polishing, the coating, and even the assembly in some cases, each has its own unique challenges. So from the growth standpoint, finding the right equipment, the right processes that are robust enough to have repeatability, which is very important from product to product, piece to piece. So that's one of the things that was a challenge. The other thing is we've been polishing material, whether it's gallium arsenide, zinc selenide, zinc sulfide, germanium, silicon for many years. But when you have a lot of different grits that are available for those abrasive polishes that you need for these materials. But when you get to diamond, it's already a hard material. So as you try to polish diamond, there's all new challenges that you have to face. So we really work on the processes and improvements of those particular areas to really understand the material and to work to find solutions. So I would say those are some of the big challenges. The other thing is, I think the challenge is still sometimes the price of the product. That's something people don't think about. Diamond is relatively expensive compared to other materials, but we do believe that there is value proposition, and as the technology continues to develop and the configurations that we can do with the materials, the sizes that we can produce, I think that people will realize, like you said before, if I were an engineer, this is a material that I would want to be considering for any of my design applications.
Right. So, it definitely seems like in order to come up with the most, ideal solutions, we definitely need to fulfill, both sides of the spectrum in terms of, having a great material, but also having great equipment in order to handle this material as well.
Absolutely.
So, as having talked about the challenges, especially on the material side, I know RFHIC is currently developing, Ganon diamond hemp devices, for various semiconductor applications. So, Dr. Lee, could you kind of share some of your biggest challenges that you and your team faced, especially on the device side?
Yeah, all of our the customer did something that comes out the newly developed Ganon diamond hemp device. So currently, our team is working very hard to make our goal. So as you knew that the RFHIC developing Ganon diamond hemp for RF application using the Ganon diamond epi wafer, we called Godai epi wafer. Due to CT niche match, the Ganon diamond epi wafer has a huge ball and warping, such same as we call Pringles potato chips, something like that. So due to wafer thickness, the Ganon diamond epi wafer was easy to crack, such same crispy as Pringles potato chip as well. So the former, we used conventional method, the bonding technology using silicon carbide substrate. But such kind of that technology can be possibly making the small quantity of the Ganon diamond, the hemp. But in the future, they technology cannot easy to accept the consistency and then mass production, something like that. So such kind of handling the issues is a big barrier to start the semiconductor processing at automated fab the line, something like that. So the dually RFHIC is developed, we call permanent bonding technology. That technology used diamond silicon wafer. We attach the carrier under the 1000 degrees C. So that means using that technology, we don't need any bonding, debonding technology during processing. As well as such kind of that technology can be possibly can remove all kind of the breakage issue during the processing due to total thickness is around 750 micron thick. So using those kind of permanent bonding technology, we believe that Ganon diamond hemp can be possibly to start of the production stage under the consistent process status.
Okay. Well, I'm definitely thrilled to hear that you and your team were able to kind of overcome such challenges, and I'm very excited to see RFHIC's Ganon diamond coming to fruition soon. So as we discuss further, it seems like diamond can be used for various applications, especially very promising features like industrial, commercial, or industrial commercial defense radars, as well as wireless infrastructure. Those are kind of promising applications utilizing diamond technology. But aside from that, diamond can be used in various applications. So Oliver, what are kind of some of the interesting applications that you have worked with or are currently working with that you think will kind of drive this tech forward in your respective area?
Sure, and we have an activity on diamond growth integration into gallium nitride as well, for aluminium nitride interlayers. But we also look at other materials like gallium oxide. It's kind of the new kid on the block that's very strongly thermally limited as well. And that's very challenging because it's not very stable in diamond growth environments, so you have to play a lot of games to make it work. So I won't say too much about the thermal because I think there are people that do more in that area than I do. We have a lot of activities on acoustic filtering. So we operate surface acoustic wave filters at around 20 gigahertz at a Q around 50,000. So these are pushing into frequencies in the 5G that your conventional lithium niobate won't operate in. At the same time, they'll handle power loads that you will not be able to do with a standard oxide. So this is, I think, a fairly interesting technology. It's very challenging. It's not easy, because you're trying to displace an incumbent technology. So fortunately, in this area, mostly it's not really possible with the current technology. And then the slightly wacky thing I just wanted to mention for fun is that we also build superconducting NEMs, right? So we make superconducting cantilevers out of diamond. So diamond is the only superconductor that has a high acoustic wave velocity, which is a bit weird, and it's a bit hard to explain in a way. But I mean that opens up some interesting possibilities. So I don't want to go off down the sort of off the tangent of superconducting circuits or anything, but it offers a possibility to entangle quantum states like superconducting states and actual mechanical states in the cantilever, which is a sort of holy grail in physics of looking for this 0-point motion. I mean, a lot of people are trying to detect. If a device is stationary, a physical device, it actually has to move, because otherwise, if it doesn't, it's violating uncertainty principle. And diamond is a route to look at that. I mean, unfortunately, there's a lot of competition in this area and very smart people. But I think the fact that it's a superconductor is very interesting because from IR detection and other applications, diamond could be interesting in the future. But this is very new, so I wouldn't want to bet anything on it.
That's really fascinating. Thank you for that. So in terms of, I just kind of want to dig a little bit deeper into this question. So I know, Dr. Bergonzo mentioned earlier about, diamond technology kind of being used for, even bioimplant applications, which, I find to be fascinating. Dr. Bergonzo, could you maybe explain a little bit more about this application and kind of let our audience know, why diamond could possibly be a highly desirable candidate for, biomedical applications?
Yeah, thank you. Of course, this is quite a very exotic type of application that really exploits a lot of properties together of diamond. So, here we talk about thin and flexible foils of diamond. With conductive embedded electrodes inside made of diamond as well. And the advantage is that these electrodes can be in direct contact with neurons or live tissues in order to enable cell signal recording or stimulation. This applies to any deficient losses of faculty like vision or hearing or brain issues with epilepsy and so on. And so all the time you need to make a long foil. Long is being for a small animal, typically 3-4 centimeter probably, or and for humans it's rather 5 or 6 centimeter. So to start with, you need to be able to grow at least 4-inch or 6-inch substrates, and on those you need to make a multiple series of nanotech lithography and so on in order to make that device. For example, you need small electrodes that are the size of neuron cells. So neuron cells are typically a few tens of microns. So you need to have point electrodes that are maybe 30 to 50 microns. And then these need to be flexible in a flexible material, because if you put a lump of glass inside the eye, then of course you understand how you will cut the tissues. Also, you need the surgeon to be able to manipulate the material in order to insert it into the eye or the cortex again. And so the applications are, these type of device existed today with other materials than diamond, and they use, for example, for monitoring epilepsy disease or things like this, but it's always for a few weeks maximum experiments. If you want to stimulate the retina for a blind person or the hearing for a deaf person, then you need basically a lifetime. Like people have done for pacemakers, you need to be able to have a device that is compatible with in vivo biocompatibility, embedded in a material that is completely, not letting water get in. And at the end of the day, these challenges are all summarized in the necessity to have a tool that needs to be capable to provide large area growth, selective growth, clean room compatible, high lithography, and so on. We have some customers doing this. I was myself involved in doing this for some years as well. There are a few companies working on this. There is one in Paris called Pixium Vision. I encourage you to go and see their website and buy shares if you want. Pixium is manufacturing retina implants for blind people. And now on the cortex, this is still a research field. We have a customer in Paris called Essier. It's a university. And there is a website on the project. They have to monitor cortex signals and also to stimulate the cortex directly to procure vision to blind people as well. The project is called Neurodiam, and .eu. Just go and have a look. Yeah.
Okay, will do. I mean that's really fascinating. I never imagined diamond materials being used for biomedical applications, let alone retina implants. So I definitely can see the future of diamond reshaping the medical industry as well. So I guess to move on to our next question. So, it seems like that synthetic diamonds will definitely have a significant market opportunity, not just, in electronics, but, also in various applications, like you mentioned earlier, in biomedical applications. So I'm assuming, having such a significant market, it's bound to have some type of technical or political issues that can hinder the advancements of certain technologies. So Dr. Bergonzo, what are kind of some of the factors that you are seeing limiting the adoption of synthetic diamonds within this market?
Okay, well, this is, I think, a difficult question, and if you ask the different panelists, I'm sure you will have different answers. My point of view is that there are a lot of what I would call sort of indirect political issues. Basically, no one now can grow big diamonds. I mean, big diamonds as big as what you have in big gemstones and so on. And these exist in nature. They are very rare, but they exist. And the fact that they have been rare much before the technology have made them very expensive. If we talk about the British Crown diamonds or the Cullinan diamonds, the British Sovereign Sceptra, and so on, these are several centimeter big diamonds, and they exist, and they've been there for a long time, and they don't have any price, but they exist, and they are much before people were able to grow diamond. If you compare this with another semiconductor like silicon, it didn't exist before, and people have considered that big wafers of silicon were, a new device, new technology, and you can do similar things with diamond, but not that big today, and that's why it's the problem is that all these material that we can synthesize in a lab or using an equipment, then we realize that these equipments may be able to provide you a tool that if you succeed to make a huge diamond, then, what do you do? Do you keep on manufacturing a technological device, or do you earn a fortune by making, gemstones? And this is really a point that everyone is always exposed to when you work on diamond growth. I give a very simple example. There is a technique called heteroepitaxy. Heteroepitaxy is a technique to take another substrate and to try to grow diamond on top of this substrate over a larger area. Heteroepitaxy stands for making epitaxy on another crystal than the crystal we are growing on. So basically, to make diamond, generally you need to take a diamond, but if you can do this on other type of materials, then you can make a large area diamond. There is a group in Germany, in Augsburg, everybody knows him, he's a rock star in the community, he's called Matthias Schreck, and they worked on this for about 25 years. In the mid-90s, they were already starting on the topic. In 2000, they made the first demonstration of the feasibility of making heteroepitaxy of diamond. And a couple of years ago, 2-3 years ago, they published an article where they were able to make a almost single crystal of 90 millimeter in diameter. So it's not like a heat spreading coating like we've been talking before, which is generally a polycrystalline. It's just like little grains of diamond. This is much closer to single crystal diamond. So they created a company to sell those substrates. You'll find it under the name Odiatech for Augsburg Diamond Technology in Germany. And the problem is that they will never sell a 90 millimeter wafer. And because if they do, then they lose their job. And if they give it to some group that can grow the Cullinan, then the other group will get much richer as well than they could do. So this is really a limitation for the expansion of diamond in terms of the fact that every time you grow something close to a gemstone, then you have to consider the fact that this material may have more value than the electronic device you may make out of it. And so this is really, I think, if one can make gemstone for diamond, it's really limiting the adoption of diamond as a technological product on the market, because the price is always there. We always have to consider that if you can make 300 millimeter substrates, then you have to think that this may have a value somehow in terms of carats and so on. So this is a problem we have with diamond with respect to other semiconductors where this doesn't exist. Right. I'm sure Daniel may have some things to add to this, because he's very close to Element 6, who is a leader on a part of the beer. So this is, every time you work on diamond, you have to consider these things.
But we have about 2 minutes left before we jump into Q&A. So for our last question, I just want to kind of sum up what we've all discussed and ask, Dr. Lee, what is kind of your outlook on the diamond industry, and what kind of applications within the RF and microwave landscape that you kind of see having the most impact?
Yeah, definitely diamond technology has a great opportunity of high power and high efficiency electronic semiconductor device market. As you knew that most of the radio frequency and microwave system need to make reduced their size as comparable high output power and reduce their power consumption. So I believe that diamond technology can be possibly give this solution soon. So I believe among those, our group can be possibly makes a Nobel Prize. Am I true?
Right. And I guess, Daniel, from a materials perspective, what are kind of some of the market opportunities that you see being kind of the game changers?
So I completely agree with one saying. I think the drive for data we've heard on the back of gallium nitride will continue, and I think diamond playing a role under the Hemp, the transistor, and also in terms of the terminator, the resistive elements of an RF circuit. And I think coming back to what Ollie said, as powers go up, there comes more pressure on the filters and on the switches. So I think there'll be some new progress and will continue to grow. I mean, it's ironic in a way. I spent the first 10 years of my research career in diamond trying to make diamond as boring as possible. My supervisor used to say that crystals are like people, it's their defects which make them interesting. And my job in element 6 was to try and make diamond really boring and the same every time. And interesting, over the last few years, obviously some of the understanding what these defects, how they manipulate the properties and how they can make a electrode or be a quantum spin qubit and how we can use that to measure magnetic fields. I think that's going to be something we see some increasing progress in over the next 4 to 5 years, especially with the boom around quantum technologies and medical sensing. I think in medical, I can't really comment on the implant application that Phillipe talked about, but I think there are already tangible products out there which are doing meaningful things in terms of measuring devices, measuring things relevant to the medical industry using diamond. So, but coming back to Stacey's point in the beginning, with diamond, I would disagree with Phillipe with some of his comments about gems. I don't think that's really relevant to the challenge for diamond. I think that the challenge in some ways, 10 years ago, it's about how you make this bulk stuff. The next 5 to 10 years has been how to do the processing and add the value to it. I think the next 5 to 10 years is all about the integration. And that, I think, Bonsang with the Ganon diamond is a fantastic example of that. If we can solve those integration challenges, then we untap a whole new potential for diamond.
Right. That's awesome. Yeah, I mean, I was thinking about, diamonds being used for, dental like crowns. So instead of gold, now they can be utilized with diamonds.
They're used in the drills, so you can get them the drills. The problem having a diamond tooth, of course, it would wear everything else away.
Alrighty. So we got about 10 to 15 minutes left on our webinar, so I will definitely open up the floor to the audience for some Q&A. Let's see.
Published.
Okay. So I have one question for Dr. Bergonzo. So how can hard materials like diamonds, can they maybe made flexible? I think you mentioned earlier about for the retina applications that the diamonds have to be flexible. Oh, your mic is off.
It characterizes the elasticity of the material. So the Young's modulus of diamond is one of the highest in all materials, again. And so just like the speed of sound mentioned by Oliver, or the thermal conductivity, diamond unmatch a lot of technical properties, and one of them here is the Young's modulus. You can make a 20 micron membrane of diamond, and it is extremely flexible. So you can bend it, and if you make it 10 micron or 8 micron, you can really manipulate it in order to get it fitting the curvature of the eyeball or the cortex, basically. Just because diamond is extremely flexible. Yeah.
Oh, okay. So the next question is there a technology overlap of DLC, which is a diamond-like coating, or PVD or CVD, that's used in thin film tools and tribological coatings to synthetic diamond growth for the thin micrometer range, as mentioned in medical applications. I'm not sure.
I can say something about that if that helps. I mean, you see an airplane behind me. One of the big drivers in diamond tools over the last 5-10 years is machining new hard ceramics. So that plane behind me is made in carbon fiber reinforced plastic. That's a very hard, brittle, abrasive ceramic. And for the plane industry, that's great because it's very lightweight. So that's what's helped to get the CO2 emissions down from the plane industry. The challenge is with the ceramic is how do you machine it? And one of the go-to solution these days is a diamond-coated carbide tool. So it'd be tungsten carbide, which has been traditionally used, but now a thin diamond coating on that. And there's the abrasive properties of the diamond means you can actually drill holes efficiently through these hard ceramics.
And I would add to that for a second, Don Daniels is, 2.6 also has different materials like thermodite out of our M-cubed area where it's hard materials. And that's one of the ideas is to have those thin films go over that material. So as Daniel was saying, they become stronger and a better option for maybe the materials that don't have that capability. So, and 2.6 currently already has a diamond overcoat that we do on certain materials like zinc selenide that is biocompatible, that is used inside the human body. So I think that definitely you're going to see that transition to some of the thin films that we're doing with the CVD process diamond that will also come into play. So I would agree.
The next question is for Dr. Lee. Do you kind of see any limitations on Ganon diamond in terms of frequency range, especially for the use for communication bands, like including millimeter waves and higher frequency ranges?
But we still evaluating how high frequency can be made using the Ganon diamond. But I believe theoretically, Ganon diamond hemp can be possibly covered up to 100 gigahertz easily.
And the next question is, in terms of thermal properties. I know diamond is probably one of the most thermally hold on a second, conductive products, but where did that question go? I guess I'll just skip to a different question. I guess a person asked, how soon will we be able to purchase fully qualified Ganon diamond transistors from RFHIC?
So I got a same question every day from my boss. Yeah, I really hope so. That's something that we still keep working, and then possibly maybe until within 2 years, we hope that there's get some the new and high qualified Ganon diamond selling to the targeting market. Yeah. To be continued, okay?
Looking forward to it.
And if I can just add to Wong Sang's previous answer, for the RF guys out there who don't know, one of the key properties that help diamond work at high frequency is very low dielectric loss. So when you think about your RF circuit, you're worried about inductive and capacitance losses. The fact it has an intrinsic low dielectric loss is one of the reasons why in an RF circuit you can push the frequencies up without compromising performance. So it's really that power of thermal conductivity and dielectric loss that pushes you into new areas.
Right. So I guess the second question I wanted to ask you, Daniel, was, it seems like there are advantages in terms of, thermal properties with respect to, again, on silicon carbide. However, at lower frequency ranges, lower than 1 gigahertz applications, considering the size of, devices, is there an advantage compared to, LDMOS technology especially for thermal properties?
To be honest, I don't know enough to really be able to answer that question. I think we have seen historically, so in in its simplest form, there's two approaches to how diamond's used to enhance thermal performance of the device. One is really trying to get the diamond very integral to the device, like growing the diamond on the gallium nitride, similar to what Ron Zhang talked about with Ganon diamond. The second is a singulated approach, or it's typically GaN on silicon or gallium arsenide, and then attaching it to a diamond heat spreader. You might attach it through a hard solder. And we certainly saw 10, 15 years ago, gallium arsenide devices performance being pushed down at the 1 gigahertz and below by solving the thermal properties. It was always a niche applications where performance really made a big difference in things like satellite comms. But there is a benefit. Often it comes down to cost per performance benefit.
Right. In terms of cost, yeah, right. So the next question is for Dr. Lee. What are kind of the power levels that are kind of available for 5G or wireless infrastructure that's capable with diamond technology?
Depend on which type of the system the customer needs, but something that we can often vary, something not only the small size of maybe the below 10 watt up to maybe the 50 watt or 100 watt. We can possibly make some same the comparable by the small form factor, something like that. So we can has a lot of the opportunity to overcome such kind of that market demand when we using the Ganon diamond Hemp technology.
Okay. So the next question is also for Daniel. So what are kind of some of the unique examples of applications for the transparent diamond coated wafer that you were talking about?
I mean, okay, so first thing, not all products are this big. I mean, often we will grow it away from be cut down much smaller. But I mean, one classic example which Stacey talked about is in high power laser systems for EUV lithography. So believe it or not, 7-9 nanometer EUV lithography is driven by very high power CO2 lasers coupling into a tin plasma. And these lasers might be 20 to 30 kilowatts. So you're coupling a huge amount of infrared power through an optical window. The diamond's transparent, but again, because it's great conducting the heat away when it's lost, it's really enabling those high power lasers and directly helping to enable EUV lithography, which we all benefit from in our phones and our laptops. So that's one example. I think that the second example, which is still technology of the future, and that's particularly what this window is for fusion, high energy fusion reactors. So where you're trying to couple something like 1 or 2 megawatts of microwave power into a tritium plasma. So you think a megawatt now, we're talking about power. So believe it or not, this window couples 2 megawatts of microwave power into a fusion reactor. So if fusion is real and fusion is the energy source of the future, that would be a very large market for diamond. And the last one, coming back to the thermal management applications, I mean, Ron Zhang talked about thermal conductivity of 1500 watts per meter K. This is around 2,200. So again, very high-end thermal management applications. This is a unique heat spreader.
Right. Interesting. So the next question is for Stacey. What's the largest diamond wafer size that can be grown today, possibly?
So depending on the application, whether it's thermal or optical, we can probably go up to a little greater than a 2-inch diameter on the optical, 2 to 3 inch diameter, and then we can go as small as 120 micron coating, depending on the material that needs to have that applied to it. So we're probably in that 2 to 3 inch diameter.
And the next question is for Oliver. What's kind of the best substrate for growing diamond?
It depends what you're trying to do. I mean, if you want to take it off afterwards, I mean, and so a lot of my background
high power electronic applications.
Oh, right. I don't really do that. I mean, I do a little bit of thermal management, and when we're doing that, we're integrating into gallium nitride with aluminum nitride on it. So we don't have control over the substrates. That's dictated to us. For a lot of the other thermal stuff we do, it's usually grown on either silicon or moly and removed from it, and there are reasons why you'd want to. Yeah, I mean, I don't think there's a best one. I mean, we use a lot of silicon because it's cheap and easy to etch, and we, like I say, we do a lot of very thin material for MEMS, and some of the acoustic devices as well tend to be grown onto silicon, and that's kind of an integration thing. Sorry, yeah. So I don't think there is a best one. I think it depends what you're trying to do.
Right. So I guess the next question is for Dr. Lee. Are diamond heat spreaders available for standard, Ganon silicon carbide devices as well?
Yeah, I believe so. Right? Yeah. Mm-hmm.
And I would just like to correct my answer. Sorry, I wanted to get back to the size of it. I was thinking more on thicknesses, but it's probably more in the 100 millimeter, 200 millimeter diameter, somewhere in that area, with some of the thickness or the diameters we can do. Sorry.
Oh, you're fine. Let's see if there's any other questions. I think that's all the questions that we have for today. So thank you everyone for taking the time today to join being part of our webinar. I definitely enjoyed being a part of this discussion, and I definitely learned a lot. Especially having experts within different backgrounds and different businesses kind of made me even more excited about the abundant possibilities and applications utilizing diamond technology. So as mentioned before, this webinar is being recorded and will be sent to you to your emails within the next 24 hours for you to view again, or if you wish to share with your colleagues. I'll also be sending out post-webinar surveys within the next couple of days. So if you could take an hour or a moment to kind of fill those out, we would definitely greatly appreciate it. So I guess that's it for today. Thank you to our listeners for tuning in, and thank you to our 5 panelists for taking part. So thank you so much, Dr. Lee, Stacey, Professor Oliver, Dr. Phillipe, and Daniel.
Thank you so much.
Hope you and all of your loved ones stay safe and healthy, and we definitely wish to see you all soon. Thank you.
Thank you.
Thank you.
Have a good day. Bye-bye.
Bye.
Bye-bye.